All right, so our lab today was Petroleum Engineering Jello Fracturing Lab. We have a little video just kind of showing you what the lab sort of looks like because it's difficult to visualize. This video, they're using a straw. This is a container of Jello, and they're inserting corn syrup. So at this particular lab, they're actually looking at different depths of inserting the straw in Jello. And so this is the shallow depth. And next they're gonna actually look at the deeper depth. And so fracturing, we want to actually create fractures within this Jello. And so here's gonna be the greater depth, which they're showing the demo of this. And the greater depth should, in essence, create a little bit more fracturing. It's a little bit different from our lab, but it definitely helps kind of visualize the process of what we're actually doing. All right, so what is fracturing? One of the things about fracturing is it's basically they call it fracking, breaking or fracturing the sedimentary rock for the purpose of increasing the flow of oil. So for this particular, there are different types of fracturing, but we're actually doing hydraulic fracturing. That's one of the most common types. And that's essentially whenever they have high pressure fluid is inserted into the fracking well. So this little visual we have here, it shows you all of the different types of rocks. You'll see you have like the shale, sandstone, and other porous rock, which would be considered the impermeable. And you also have like a well. So petroleum engineers have to actually design the well. And they also have to insert this particular type of fluid into the well. And the whole purpose is to basically crack this impermeable sedimentary rock. But there's a lot of problems. If you guys are looking at this visual, you could probably see you see wastewater could be transported, and then there are problems that can cause earthquakes. So that's kind of where this next slide goes. We have some of the pros. So some of the pros, of course, are you're gonna have like a lot of this oil, we're going to be able to actually like bring it to the surface because we wouldn't be able to bring it to the surface if we didn't do fracturing, just because of the way that this impermeable sedimentary rock, we got the shale, sandstorm, all of that, it just is not easy to flow. It doesn't make the oil easy to flow. So one of the pros, of course, is we're going to have more supply and then we're going to have lower prices. So it's good for the consumer. However, cons, it could be really bad. They could be earthquakes. You could have contamination. You could have a lot of safety hazards. So there's a lot of like controversy with fracking. Some of the safety hazards, part of it is like waste. There's a whole bunch of processes that I never knew about petroleum prior to like this lab. But basically, you can have like, of course, like falls, fires, explosions, gas leaks, contamination of the environment, damage to the ecosystem. So a lot of these other safety hazards you'll have in other engineering, especially like chemical. However, contamination of the environment and damage to the ecosystem, I think that those are kind of more specific, more to hydraulic fracturing. And we actually like did demonstrate contamination of the environment for our particular lab. So you really don't want to basically drill too deep, or you want to make sure that you're kind of controlling where your fractures are going. You want to make sure that you're controlling honestly every stage of the process. You want to make sure everything's pressure controlled, everything, so that way you're not damaging this water, because that really could cause a lot of detrimental effects. All right, so impermeability. I know it doesn't probably make a lot of sense, I suppose, I guess because I didn't really like study a whole bunch of rock in my undergraduate experience. But I really like kind of thought about like what's the whole purpose of fracturing. And basically impermeability is they're talking about the resistance of a rock to basically like allow fluids to flow through it. The scientific term is flux. And so basically the whole purpose of fracking is to increase the permeability of these rocks. So you could have like shale, you could have sandstone, limestone, carbonite, whatever you want to call these sedimentary rocks. And so you are basically creating and connecting the fractures, and then they just enhancing that oil. So you'll see you've got water, oil, gas, and then above, like close to the surface, you've got that rock, which basically makes it really difficult for that oil and gas to flow through. And then it's so easy because the water is so close to contaminate. So we just want to be really careful through the whole process of it. All right, a little bit of introduction about petroleum engineering. So basically, petroleum does incorporate the work of a reservoir drilling, completion, production, facilities, and chemical engineer. Of course, environmental as well. But basically, the engineer would essentially extract oil or gas through this rock, and you don't want to cause harm to the environment or contaminate any of the water. And then a reservoir engineer would find the oil. So there's a lot of different specialties. It seems like it's extremely specialized, and one person does all the equipment. They understand all of the I guess like geological factors of the environment, like, and all of the different things that they really need to control for it. I mean, it's really, really heavy duty machinery. It's super expensive. All right, so our project, we actually had to, for our jello fracturing lab, we had to demonstrate the role of a drilling engineer. That was the part one. So a drilling engineer, what they do is they design and they implement procedures to drill wells. So wells essentially is just this hole in the ground that we've got. And so after you have wells that you're doing to drill oil, and they want to basically make sure that they are creating them safely, economically, and there are vertical wells. So for the sake of this lab, we're doing a vertically fractured well. And our goal for the lab was to decide the location for the well. And then we wanted to determine the best way to reach the oil without losing control. So losing control of the well would mean contamination. All right, so our second goal for this actual experiment is we were had to act as the completion engineer. So the completion engineer is they basically had to design, find a way to design and finish the building wells so that hydrocarbons is another word for oils. Oils can flow up from underground. So basically they have these perforations, which is actually going to be a huge part of our lab. They have all these, it's basically like these little holes that we drill, or, you know, for us, we actually just poked holes and we wanted to see what was the holes, best configuration for poking holes into this well that's actually going to allow permeability and fracturing of our oil reservoir. So they'll use this word well bore, and I believe I have a picture of that. Yes, here it is. So we've got well bore designs. This is actually like a really, I mean, I honestly didn't know about this either. This is a whole thing of designing this actual well bore head. So one of the things that you want to look for is you want to look for perforations. When you see these little dots, you can kind of see it, but it's very technical. There's a lot of different pieces. You got a sleeve, you've got, I mean, it's not just a hole in the ground. Like they have people who study and they create designs for this. The size is important. So you could have like a more narrow or more bigger. The location of where basically these are put in the ground. You also want it to be nearby oil reservoirs. And then also are you going to inject fluid at a high pressure or a low pressure speed. So these are all things we're going to actually modify in our lab. And these are the people that we acted as in our lab. And the materials, basically, we have 2 containers of Jello. We used a syringe, cane syrup, vegetable oil. We had straws, tape, push pins, scissors, and then some of the constraints, of course, are materials, time, and design. And yes, this is actually kind of segueing into what we actually did for our lab and how all of that connects. We use the Jello as basically our rock, and then our straws are going to be essentially like our well. And then we went ahead and designed our straws, and we put preparations, And then we also controlled for this injection speed, just so that way we could pretty much act as like these engineers.
All right. So here's another picture of the materials. So we had the with the green jello, that's like the first well that we had. And then the yellow jello, that was the backups that I had. And so as you can see here in the first picture, that's the yellow jello. And then the next one, the green jello, that was the first one we that we used. And then in this next picture, I'm showing that I'm using the injection, and I'm using one of the boba tea straws. We're trying to see the difference on how well this injection fluid can go in. And this last picture is a picture of all the straws that we used on the first test. All right, so the procedures in full, as a drilling engineer, you have to either glue or tape one end of the straw closed by folding the ends over twice and securing it with either glue or tape. So I tried it with regular Elmer's glue, and that didn't work. So I had to use the tape. But going forward, I know that if I'm going to glue it, maybe hot glue probably would be the best thing. And so, as a completion engineer, you're going to poke holes in the straws in a 0 degree, 90 degree, 180 degree, or 360 degree configuration. And then you choose which one you will use for trial one. So in the 0 degrees, what it means is that the holes are all on one side. For 90 degrees, it means you're going to poke it on two sides, but it's going to be a fourth of the way apart. Then for 180 degrees, it's going to be on both sides of the straw, but they're going to be half the distance on the straw. And for 360, it means that the straws are going to be literally the holes are going to be all around the straw. And so it says the next step, you would place the straw in the jello, then you pump the syrup with the syringe, you record the rate of syrup, the number of holes, and the degree of holes in the table. And the jello mold should be at least 750 milliliters in a 750 milliliter container. The reason why I'm stating that is because the first container we used wasn't exactly 750 milliliters. And so it was really shallow, but we still were able to be effective though. And then after you have pumped the syrup inside of the straw, then you pull the straw out of the jello and observe the areas of the fracture and see how far it went. And you want to, that's how you determine whether or not if the penetration was a success or a contamination. And then lastly, as a reservoir engineer, because I'm just basically combining both one and two together, the last thing that you would do is you figure out which straw model didn't do as much damage but was effective, and it dispersed enough syrup successfully with the jello reservoir, which has oil that has at least about 2/3 of the way into the mold, and by having as little contact with the vegetable oil. And your vegetable oil are your hydrocarbons. And at some point, the fracture fluid will reach the hydrocarbons, but you don't want it to reach it immediately. Because I noticed, after a day, that's literally what happened. So some of the brainstorming ideas, this graphic is showing you guys what we looked at. That's showing you the 0 degrees, the 180, the 360 on the perforations on the straw. And some of the other things that we had to look at was the injection speeds and the location of where the perforations were. If the perforations were too high, you only made a mess. It didn't go inside of the mold. It just went all over the Jello mold. But if you put it where where you were going to put the straw in the entry point, that probably not probably that was the best part to put it, the best area to put it in. So in the next slide, we're showing you guys the results. So in trial 1, we had 6 holes, and the holes were in the medium area, and it was the 0 degrees. The injection speed was slow, and we used a smoothie straw. We had some fracturing with that. Then in the next trial, it was 90 degrees, and we had contamination because because it was a little too high. Sadly, the perforations were too high, so it got kind of all over the place. In the next trial, we had contamination again. So with the fourth trial, it was slow. We had some fracturing, but that one was messy too. Sad. I'm sorry to say it. The fifth trial with the 180, I don't know why, but it went in really fast, and we had medium fracturing. So we had a decent amount of fracturing. For the sixth one, it went in. That probably went in the best. And then you had for 7, 8, 9, and 10. These are the ones that I did in the yellow Jello. And once again, with that one, because I had more space, I didn't have any contamination, but I was able to see just how fast the fracturing was. So my last two, the 90 degree and the 180 degree, it took a while for it to permeate, because it looked like it didn't permeate at all, but it took a while. And so once it finally started coming out, it was successful, and thank God it didn't go to the bottom. All right, so here we're showing you the results. So the first mold in the green one, you can see where we had our contamination over here, where there's a lot of cane syrup in this area. And then the rest of them, you can see where it fractured out. It fractured out a good distance, but one was very close to the edge, so that was almost a failure. And then here, that's me showing you all how I injected it. And then the last ones here, I'm showing you how the syrup came out. And in these two, it was kind of slow in permeating, but it did eventually do so. So in the next picture, yeah, here it's I'm showing you guys, I had to get close to it, the permeability. Thank God it didn't go to the bottom, because that was one of the main goals. And these two here, those are the bobas. Like I said, that came out very slowly, but the green and the blue one, it came out the best. And those perforations were 0 and 360. All right. So here is the last one. So it says our goal is to fracture the Jello so the syrup will create permeability in the Jello and be able to reach the oil reservoir. And the fracture fluid should show up in a hydrocarbon reservoir. It did do that like maybe the next day, but it didn't do that immediately. So you can see here in the first one, this is the oil in this area here. And that's the same thing in the green one. We're showing you the oil. You could see it. And we used the 0 degree for the 0 degree straw for the perforation. And it was the same thing that I used on the last one in the yellow. I used the 0 degree straw, and that one permeated the best. Okay, so the discussion questions. It says, what were some of the changes you made to your well bore, and what did you do differently, and why did you do this differently? So in the first model, the reservoir, as I said before, was a little too shallow. So the next reservoir was the recommended 750 milliliters as recommended. And this was done in order to fracture the mold properly. And the second time, all holes were near the bottom of the straw in order to reach the well instead of them being mid-level or top level. And then the second question asks, once you redesign your model, were your adjustments successful? What worked and what didn't? If you were to redesign again with unlimited resources, what might you do differently? So the adjustments were successful. The 0-degree perforation design worked the best. And if I were to do anything differently, I would add color to the vegetable oil so you can clearly see that this is the vegetable oil. That probably would be one of the things that I would do. And in the fracturing process, you must consider your setup and cleanup and how these two processes impact the environment. So you discuss in your report what you think would be a good way to mitigate environmental concerns about fracturing. All right. So I wrote just a little bit of sentence here, but it's way more than that. So it says, there are concerns with fracturing involve the groundwater contamination. That's one. Air pollution, loss of habitats, a clean system for fracturing would be helpful. I know I was, excuse the brevity on that, but okay. As my colleague stated, they believe that fracturing leads to earthquakes. Now, the industry will tell you that that's not true, but they don't know that yet. And that's just the truth. The next part about it is, one thing they do know, but they try to say that it's not true, is that groundwater definitely gets contaminated. And so one of the biggest things that they're working on is trying to make sure that the groundwater does not get contaminated. And then the last thing is that they're probably not talking about yet, sinkholes. You got to bear in mind, you are going through these levels of shale, you're going through these levels of rock, and at some point it's going to sink in. Now, no one's talking about it yet, but sooner or later somebody's going to think, there's an oil well so many miles or so from here. I wonder if that's causing this indentation in the ground. Who knows? All right. And there's about 1,000 more things I could talk about, yet I digress. I'm not even going to talk about how they're going to, wait it out to buy the land from people who are sitting on these $1 million shells. I'm not going to talk about all that. I'm not going to talk about how they're going to go to Titan and try to get the oil that's on that moon. I'm not going to talk about that. Talk about the things that they can do right now. And then the last question says, brainstorm ideas of how you could make this model better. What materials might you need to make this model more accurate? And how many extra steps would you add to the procedure to improve this model, and be sure to justify the adjustments? So there would be more perforations and a better seal. Also, we would look at drilling for more depth into the jello. And yeah, I've already figured out that the best seal would be hot glue. And if there's some extra steps, no, I think it's pretty good the way that it is. Yeah. And that's it.
Awesome. Thank you so much. Any questions for the team before I jump in? Yes, Edie.
So I was writing down things you were saying, and like materials we would need. First, how did you poke holes in your straws?
Oh, I'm so sorry I didn't say that. I poked holes in the straws with a push pin.
Okay.
I will say this. You could have the hole. You could have had a hole as big as as if you used like a hole punch, because that would have been a really big hole. I didn't want to try that because I just didn't want to risk I just didn't want to risk it. I'm being honest. I didn't want to risk
Right,
it.
right.
But you could use that as well.
Yeah, some people use scissors to cut out like a little notch, but yeah, like Roshan said, like what they found, the push pin size, like if you get too big of a hole, then there's the syrup is going to start to leak out before
Mhm.
you even like push your syringe down to force the syrup out. So it's okay for the kids to try that, but it won't work very well.
Right?
Okay. One more thing. So if we're looking at setting up our classroom,
Mhm.
in workstations for this lab,
Mhm.
so we probably need some paper towel. I was just want to know like paper towels and how do we keep the Jello? How you think we're gonna keep the Jello cold? Because I already know my schedule. My kids come in at 5th block, so it's our 4th block. So it's like so I'm just thinking of all the things to do this lab. And so paper towel for sure. What else would you recommend us getting ready for the kids in our classroom?
So what I would recommend is if you have access to like a cooler at the in the cafeteria, or like in our teachers lounge, you could put it in that refrigerator. That would probably be the best thing. Now, one of the things that me and Christina was talking about is, should we allow the kids to make the jello, or should, we prepare the jello ourselves? That's something that you're just going to have to wait and see. I will recommend that make sure that you have that jello done the night before, because it takes a while for the mold to set straight up.
Yeah. Yeah. I mean, I think typically most teachers are, make the Jello. So transporting it back and forth from your home is hard. So typically what the teachers will do, because you need hot water to dissolve the liquid, is if your chemistry lab or one of your science labs has like a hot plate or something, that you would, make the Jello in the chemistry lab, and have make the containers and then put them in your fridge, like if you do have like a teacher's lounge or something. And this is one, because especially if you've got a large class, you could have teams of 4,
Mhm.
because essentially what you could do, and here, Roshan, if you stop sharing your screen for a second, I'll show this piece of paper that I have. So essentially you could have, is that backwards? That's backwards, huh? Why is
No,
it?
it looks good.
It looks good. It looks backwards on mine. Okay. So essentially you would have, you could have 4 team members and say person number 1 has design number 1, person number 2. And so this is your straw, right? And so you've glued or taped the bottom, right? But you don't want any oil to come out of the bottom of the straw, right? So you kind of fold the straw lightly and then somehow secure it either with tape or hot glue is the best, right? So person number 1 decided they wanted 3 medium-sized holes, which would, if you have the push pin, if you just barely poke it, it would be maybe small, but if you push the push pin all the way in, how the pin is kind of tapered at the end, right? So maybe pushing the pin all the way in and kind of really getting it in there. So person number 1 on the team is going for 3 holes with a 0 degree, because they're all on the same side, and medium size. And then they also get to decide the size of the straw and the injection speed. Okay, so the syringe is attached up here, and they're going to decide if they're going to push the syringe fast or slow. Okay, then person 2, this is their design. So 180 degrees, medium size holes, 6 holes. And then they also decide the size of their straw and the injection speed. Person number 3 has like 360 degrees with lots of teeny tiny holes. And person number 4 decided to go the hole punch method. So they have 1 hole that's a hole punch. Okay, so this is how you could set it up to have 4 people on 1 Jello mold. And then basically they're going to go here to their Jello mold, right, and put their straw. So each person's going to get 1 spot on the Jello mold to insert their straw, right? So person number one's gonna test, person number two is gonna test, person number three is gonna test, and person number four is gonna test. And what you're gonna end up with is, so if this is person number one's test, right? So this was the 180 degrees. When they have their syrup, right? So all of this is filled with syrup. Oops, sorry. All of that's filled with syrup. Okay, and they're going to inject it, and the syrup is going to come out of these holes. And so each of the four people is going to test their jar, or their straw rather, and see what happens to the injection fluid. And so here what you should see, all of the injection fluid is going to come out in a line, right? And so the top view of this, sorry. So you've pushed the jello out, or the syrup out, it's going to come out in a line. So what you should see is a fracture that kind of comes out like this. So you saw it a little bit in the jello molds that they had. Sometimes with the colored jello, it's a little bit harder to see it. So I would recommend like the clear gelatin, but you're going to have, you know, the jello coming out in a line. The ones that have the two-sided, you know, the jello. So person number two decided to have perforations on both sides. Theirs, the syrup is going to be injected down, right? And the syrup is going to come out on both sides. So what they're going to have is fracturing this way and this way. So what you're going to end up seeing is probably some contamination, right? Because they've reached this wall when really their goal is to reach, you know, the oil that's going to be in the middle. Right? So this is the well bore where the oil is that they're trying to reach. So you don't want to reach the walls, because the walls means you've, you know, contaminated the environment. So in the initial trial, we typically don't have the oil in the middle. We're just trying to get them to see what happens to their fractures, right? So that's why they had kind of trial 1 and trial 2. So you're basically testing these 4 straw methods with the goal of trying to reach oil that would be in the middle. Okay. And then you'll get results like this. Okay. So this is just showing the result from 2 different possible scenarios. And so one with the holes on 2 sides could result in contamination because you've maybe reached the wall. And then this one where the perforations are all in one direction, you know, they're facing the oil that you're trying to reach, that might be best. So you have 4 team members. They've designed 4 different types of wells. And then one of them will go to the last day, and you can test the best method kind of one final time with the oil actually in place to see if you can reach the oil with the best method that was used. So that's kind of like this is the resource that I'm going to add is like, I'm going to make these drawings better and probably on the computer to show those steps, because we have it in words, but you know, we're going to put it in the teacher notes. And then, you know, essentially what you could, there's so many different combinations, so that basically like no one in your class is going to have the same exact well bore design. So you should end up, you know, if you have 16 kids, you could have 16 completely different, you know, different designs here, different straw sizes, different speed of injections. And I will say that I'm really surprised at how well it worked with the shallow bowl. Because, you know, you don't want the straw to touch the bottom of your container, right? Because that's also contamination. So typically we recommend like those Ziploc containers, like it's the 32-ounce Ziploc Tupperware that has the screw-on lid. I think that's what's linked into the supply thing. So they come in like a 3 or a 4-pack at the store. And that way, again, because it's got the lid too, it kind of makes it a little easier to transport them from your chemistry lab where you maybe made the Jell-O into your teacher's lounge where you have the fridge. This project is messy. It does require prep from the teacher standpoint. So a lot of people prefer to do the oil derrick, which is in one of the alternative projects. So this is basically, it's a little bit more of a building. So I would equate this project similar to environmental engineering, where you're testing out different methods for efficacy. And in future summers, I don't think that I would give those same two to the same teams. I didn't really think that through, that you guys had both environmental and this one, and then Edie and Sandy had 2 physical builds. So I would probably switch that out to give 1 and 1. But yeah, the oil derrick project is kind of more hands-on. So you use kind of balsa wood to design a derrick, and they have to be able to or not balsa wood, I think it's toothpicks. I mean, you could use whatever material you wanted, but essentially they have to design a derrick that can extract oil out of the ground. So that's less messy. But I think that, you know, and people have been like, why do we have to do this Jell-O? And it's true, like the kids really get a lot out of it. Like, and it's truly like very, very true to real life. I mean, it is absolutely what is happening. And then I did just want to touch on the comments that Roshan made at the end and that Christina made at the beginning with some of the slides. So fracturing is controversial, okay? And I think that that's important to talk about in your classroom, right? And I think that, you know, especially if some of their designs do contaminate, right, by touching the sides or touching the bottom, you know, that is a definite real risk. There are risks of earthquakes. There are risks of these things. And so, you know, I think it's important to talk about and to let the kids form their own opinions, essentially. But, you know, to present both sides, you know, the pros and the cons and the benefits that we get versus, you know, some of the downsides. I mean, there's, you know, to use AI, right, or to use technology, you're using servers, and servers have to run somewhere, and servers are bad for the environment because they heat things up. But would you want to give up your cell phone, or would you want to give up, you know, your computers, right? So there, you know, everything that we do has a trade-off in society. And so I would just encourage you to facilitate those conversations with your kids to, you know, kind of weigh pros and cons, and to not necessarily say like one thing is good or one thing is bad, but to say that there's always kind of 2 sides to a story. And, you know, while you might not agree with something, you know, you know, there are, you know, you might not agree with it, someone else might agree with it. And it's all about taking a stance in your beliefs, and then helping to change policy when they get old enough, right, to try to go more towards what they believe. So yeah, any other questions or thoughts about this project?
Well done, guys.
Yeah, excellent. Really, y'all nailed it, truly. Sometimes this project, when you get to the teacher notes and to the student handouts, you can probably ask Roshan and Christina, and they'll be like, it wasn't very clear and it was kind of complex and complicated, which is why I had those drawings and why I'm going to try to add some additional resources, because it is kind of hard to describe in words on paper what you're asking them to do. And then there's kind of like the part 1, part 2, because part 1 is like you're trying the different methods. And then part 2 is like, okay, you've found one of the 4 methods is the most effective. So now you're going to add the oil well that you're actually going to try to reach. So yeah, Edie.
So I'm, because this is the first, I mean, I didn't do this one and look over it. So all the, you shoot all the dye, I mean, the syrups in, then you put the Jell-O back in the fridge?
You
And
get
why,
in,
oh no, you just
you get
leave
in-
it? Because you said you came back the next day and you could see how it had moved, or like how, and it's like the results were later contamination, or like it did reach it. How how long has to pass before they look at it again? Because then the bell's gonna ring, and what do I do with it so they can see results?
So for me, mine was basically continuous because I left mine out, and when I came back to it the next morning, I saw where it had finally reached
Okay.
the oil part. But initially, you can just see the fracture, and it only goes so far. But over time, I would say maybe 4 to 6 hours, it'll get to the point where it's trying to go. And
Okay.
it does recommend that you use the 32-ounce jar
Uh-huh.
or Ziploc container. Now, the one that I had was 25 ounces because that was the one that I found. But the point being is that you want to make sure that you've got enough depth,
Yeah.
that your straws, you can try to put the perforations everywhere, but if you want to contain the mess, try to have the perforations like right where your entry point is. That's what I found out to be the best. Oh, and
Yeah.
one last thing I forgot to mention. In the instructions, when you do the second part, after you figured out which straw works best, you only have one shot. So you got to make sure you put it in the right way and make sure it doesn't contaminate. So
So
Yeah,
don't put it in the fridge, keep them out.
Well, so that's actually a really interesting point. I've never had someone actually do that. I think it's probably partially because the Jello is melting, especially if
Yes.
you left it out. So I would say that, what you should be looking at is the snapshot of what happens right away, right?
Right away,
Because in real life, like your rock is not going to melt or go away. So in real life, you kind of, you have your well, and then you inject that fluid, and that fluid is going to burst the rock. It's going to be kind of like a one-time like fissure fracture, right? And the question is, did you reach your oil? Because you don't really get like more opportunities to create more fractures. It's kind of a one-time shot. So although you did have that experience by leaving it out, I think that that's probably more that the Jello was melting as opposed to like more fractures happening. So it was an interesting observation, but I think that for the purposes of the class period, that what happens 4 to 6 hours down the road, I wouldn't consider like part of the experiment. So, you're injecting it, you're saying like, did my fractures go where my oil would be, right? And like Roshan said, you get one shot for the part 2. You kind of have said, okay, of these 4 designs, this one's best. And you want to make sure if you have all your holes in one line and you face that line towards the wall, right? That's going to be a contamination. You got to face it towards where the oil is in the middle of your Jello. And then, yeah, definitely putting all of the holes. I mean, you want your holes to be down where the oil is. You don't want your holes to be up top. So, yeah, Edie.
And it tells you how to put the oil in there, because now I'm thinking a tall, because we were looking at your bowls. So if we had a tall, and it tells you what to do to get your oil
So
low,
you
and then
you stick a straw in, you put your thumb on the top of the straw, and you pull out the Jello. So you basically are pulling out a column of Jello, and then you put the oil in there. So, we don't put the Jello back on top of it, how it would be in real life, right? In real life, the oil is under the rock. So you're basically leaving the oil exposed, but that's, you're essentially burying the oil in the thing. But that is described in the notes.
So one thing we also did is like we did cut like a little tiny straw for the shallow Jello, because I decided to use one Jello to make 2 bowls, because like we kind of wanted to get it done as early as possible, and I was hoping that it would like be quicker, but it really wasn't. But I mean, like using a little small straw, like that is another like kind of like cheat sheet you could kind of do. But still, we were really careful, and I mean, I'm not sure how the students will be.
Yeah. And if you look in the teacher notes, there are some like different things that will make the Jello more or less like kind of successful, I guess. So the recommendation is like a half a cup of water to 3 packets of gelatin. So it's got very specific instructions. If you don't have that and you just make like regular Jello, it'll work too. But like regular, like whatever the proportions are that are on the regular Jello, excuse me, bless me, thank you. The whatever the instructions are on the regular Jello, I think that if I recall correctly, it is it's a little bit looser. So I think in our recommendations, the half a cup of water to 3 packets of Jello, and then the 3.5 cups of boiling water, that ends up making a little bit of a thicker Jello consistency than what's on the recommended packet. It works both ways. It's just by having it thicker, it holds the fractures better. It's just, you know, so this is one where having the right materials is like pretty important. As you saw though, they were able to do the experiment with, you know, different materials, like just the bowl, like having a shallow bowl, but it works significantly better if you have clear gelatin and if you have, you know, a tall skinny container.
And it also recommended that if you have access to just the regular agar, because that would be completely clear, but just like she said, a clear gelatin is the best thing. So I used yellow Jello. I don't recommend red.
Yeah.
But yeah, the clearest color you can find, that's what I recommend.
Yeah. All right, great. All right, we have our last group. Let me stop the recording.